Welcome, quantitative analysis students. This is Mr. Marquetta, and I'm here to help you with Chapter 5.1 out of our submodule 5A here in summer session B. We are wrapping up our summer session. We're at the end of our lessons. We have this one, and we have another one after this that we'll talk about in this PowerPoint in this video. Chapter 5.2 is going to be in this video as well. And then tomorrow is our last lesson, which is 6.1. Today is June 21st, 2021, and I thought that it would be fun to share with you some of my favorite places. This PowerPoint I created with photographs that I took of my own of places that really mean something to me. For example, this is Bayonne Park. Bayonne Park means something to me because I grew up in Bayonne, and this is probably the nicest place to go in Bayonne. It's right around 34th Street or so, and you can go and check out the water here. And if you're in Bayonne, I do recommend that you take a minute and drive through the park. It won't take you a minute, it'll take you a little while. It's a big park. All right, so today's lesson will include all kinds of fun pictures like this. Our next one, of course, this is Egg Harbor City Lake. This is about 2 miles away from where I live, and I go here all the time and go swimming here all the time. It's a great place. It makes you think of Camp Crystal Lake from Friday the 13th a little bit, but it's a great place to go swimming, and the kids love it, and it's a local fun place to go. So today we are going to focus together on exponential functions and logarithmic functions, and I want you to think of logarithms and exponents as inverses, the same way we think of times and divide, and minus and plus are inverses, exponential and logarithmic are inverses. In order to have a good grasp on logarithmic connections, you should have a good grasp first on exponential connections. And exponential ideas are really not that hard. It's just a matter of taking a number and raising it to a power. There are all kinds of adorable little axioms involved. Like, for example, if you raise something to a negative power, you actually shrink the number. Whereas if you raise something to a positive power, you're going to increase the number. And that works particularly with positive numbers and also with other special sets of numbers, things like that. But when it comes to exponential functions, you have to know how that works with positive and negative exponents. And you also have to have a little bit of a grasp on what fractional exponents mean. And it's easy to confuse the two and to, by accident, use the property from one on the other, because fractions and negatives kind of find themselves being kind of inverses in their own funny way when it comes to exponentials. Anyway, try to keep it as basic as we can, and let's talk about it in its most simplistic way. What is an exponential function? An exponential function is when you have a model that is some number to the power of x, meaning that the independent variable x is the actual exponent. Sometimes it's not to the it's not to the power x, it's to the power 5x or to the power x minus 8 or to the power minus 2x or something like that. But in other words, the point is the exponent is, the variable is up in the exponent. Also, sometimes you have a multiplier, like instead of it just being 5 to the x, it might be 3 parentheses times parentheses 5 to the x close parentheses. So in other words, you might have a multiplier out there too, and you'll see that in the syntax of Desmos when we start doing regression lines with exponential functions, which we're going to do today as well. So let's focus now on these little ideas associated with exponents together. First, it says the variable a is any real number. So for example, I have the case of y equals 2 to the x here, so that you could see what happens when you're looking at x and y values for a function at its most basic form. An exponential function like 2 to the x is the most basic kind of exponential function there is. The x-axis represents an asymptote, okay? And before we talk about that, let's talk about these points. You'll notice some of them are very easy to understand, like 2 to the 0 is 1. That's a definition you learned a long time ago. Anything to the 0 is 1. 1, when you use 1, if you look there, 2 to the 1 power is 2. The next one, 2 to the 2 power is 4, and so on. So in other words, these are very clear to us. I'm pretty sure everybody's really comfortable with these, you know. Pretty easy, and we all understand how exponents work. But then, you know, we may not have taken these advanced math classes or remember these advanced math classes to the point that we know how to deal with negative exponents. So I'd like to focus your attention first, guys, on this one right here. It's easier to try to understand this one first. You'll notice that it's raising to a negative power. At a first glance, you look at that and you think that's impossible. How can you raise something to a negative power? You know, it's kind of like your mind resists that a little bit. And that's natural because the only definition we know about powers is to take something and raise it to a power means multiply it by itself that many times. Well, how could you multiply something by itself a negative amount of times? You kind of can't. So instead, we have a definition that we use as a shorthand, and we have to kind of just believe it for now. If you would study more advanced mathematics and you go further into it and delve into the reasoning, you'll understand why negatives turn out this way with exponents. But for now, it's okay to just kind of accept it for the way it is. And when you see something like -3, I want you to think about it as if it's +3, but then just take the reciprocal. That's all it means. So when you look at an exponent and it's negative, you can pretend the negative is not there for a minute, find the answer, and then flip it. So for example, for 2 to the -3 power, well, 2 to the 3 is 8. So let's make it 1/8. Let's focus now on what if it was -2. I'll use purple for that. So 2 to the -2. Well, I know what 2 to the 2 is. It's 4. So since it's -2, I'll flip it now. It's 1/4. And last but not least, of course, we have the -1 case. And if it's -1, you'll think of it, of course, as 2 to the 1 is 2. So the reciprocal is 1/2. Okay, so negative exponents mean just do it and then take the reciprocal, and you'll always get them right. Now, the other thing to talk about here while we're in this conversation is when you use the calculator, sometimes it depends on what kind of negative button you use. If you take a look here at this calculator with me, and I'm going to try to have it focus with you on the other camera for a minute, because I want to talk to you a little bit about a calculator right now. All right. Now, if you look at this calculator with me for a minute, you'll see that there are two important buttons I'd like to point out to you. One of them is right here. I don't know if you could see it. It's kind of blurry. All right, but it's right here. It says plus minus. See that? Plus minus. It says, I don't know if you could see it. Also, there's another button here that's a minus button. See that? Different calculators have different buttons that mean different things. If you want to tell the calculator -15, you'd have to first put on the calculator, type in 15, and then toggle it from plus to minus by pressing this button. See how the negative appears? If you start by putting in -15, sometimes calculators don't do it what you need. See, I typed -15, it didn't come out as negative. This means when you're joining together two numbers, so to make it negative, I have to use this button. And it's really important that we're comfortable with that idea. See how it toggles back and forth? You can make anything positive or negative back and forth with that button. And not every calculator has that. Some calculators have different kinds of buttons like that. But the point is, anyway, when it comes to using your calculator to get negative exponents, that's really kind of an important part of it. And if you're not familiar with how your calculator works with negatives, take a minute and go to take a minute and go to YouTube and just Google your calculator's name. Like this one is called Electronic Scientific 10-digit. It doesn't even have a model to it. It's the cheapest calculator you can find. But the point I'm trying to make is, like, if you put in a model number of a calculator and type in negative, positive, it will tell you how to use it properly with the negatives. And I recommend you do that, or if you're doing it in Desmos, you have to worry about any of that at all, of course. And we are going to do most of this with Desmos anyway. But see, these are the things that would come into play if we were in a classroom where we were using calculators. So anyway, negative exponents work in the way that I explained. And then the way that exponential functions work is if you just carefully plot all of those points according to those rules of positive exponents and negative exponents, whether you're using a calculator or a graphing utility or something like that, you're going to get this interesting shape. It looks kind of like a boomerang. Right. Here we go. Right here, it's like a boomerang. It's coming up. See it? And they always have that bend. It's like a bend that way. And you'll notice it's shooting up very fast on the right. And it's really getting closer and closer and closer on the left. I want to focus your attention right here, right now. Look over here at this part of the graph right here. See how it's getting closer and closer to the x-axis there? What happens is, if you imagine like -3, the measurement was 1/8, right? So -4 is going to be 1/16. And -5 is going to be 1/32. And -6 is going to be 1/64. And think about how that fraction is getting smaller and smaller and smaller. Now let's get theoretical. Will it ever become 0? No, it won't. Even if it's like a million, right? What is 2 to the -1 million? It's not 0. I mean, it's extremely small, but it's not 0. And the point that we're trying to make is you will never ever touch the x-axis with a boomerang curve like this, with a exponential. And that's something we call an asymptote. An asymptote is a line that is there on the graph. That it's not part of the graph, but you can draw it in as a boundary line because the graph will get closer and closer and closer to it, but will never ever touch it because of some property of arithmetic, like exponential functions, for example. There are other cases of asymptotes when you study hyperbolas, and some other interesting functions have asymptotes. And in the case of an exponential function, this is an asymptote, the x-axis. Also, There's something else that's really important about every exponential function. The boomerang has not just a asymptote, it also has what's called a central point. Different books call it different things. I like to call it a central point. I saw that somewhere in a book and it made sense to me the most. Think about how a parabola has a vertex, or how a circle has a center. Well, an exponential function has a very important central point, and that central point is right here. I'm going to highlight it for us. Here's your central point, 0, 1. And the reason why that's a central point is because anything to the 0 power is 1. So regardless of what your base is, if it's 2 to the x, or 10 to the x, or 99 to the x, or 1/3 to the x, or anything to the x, you're always going to have that same point, 0, 1. And that point can be moved around with translations. If you do a translation, or if you do a reflection, or if you have some kind of variation of an exponential function, of course it'll move. But in other words, when you move it, you can use that central point as your guide of where to move the central point and let the graph fall then where it is. Same way you'd move the vertex of a parabola when you were translating it, or reflecting it, or rotating it, or the same way you would move a circle or something else, or a vertex of a polygon. So I just want to reiterate, for exponential functions, it's important you know how plus and minus exponents work. It's important you recognize that there is always going to be an asymptote. And last but not least, it's really crucial that you recognize that there is a central point, and the central point is common to any base. Now, with this, you can stretch it, you can move them, and so on. This is a very basic one where the x-axis happens to be the asymptote. Please do not assume that the asymptote is always the x-axis. That is not the case. The asymptote is simply one notch down from where the central point is, or however multiplications down according to a dilation, if you have a multiplication in there, which is stretching it in those cases. But the same format does apply. You have that central point, and then you have your boundary line, which is the asymptote, and then you have a boomerang-looking curve in it that's going up very sharply in one direction and getting closer and closer to the asymptote in the other section. You may recall walking past here at Monmouth University. This is a place called Erlanger Gardens. Right behind Erlanger Gardens, you can see the College Center over there. This is a really great place when we have fair weather to kind of hang out and study. You could have a seat on the steps there and read a book, or hang out in the shade. The fountains provide all kinds of therapeutic feelings and all that good stuff. So this is called Erlanger Gardens. All right, and now let's talk a little bit about logarithmic functions. Now, I want you to think about logarithmic functions, like I said earlier, as they are the complete inverse and opposite of exponential functions. And I want you to look right now at the table we have here. Take a look at this table with me. Don't those numbers look kind of familiar? In other words, they're everything we just saw, but backwards. Instead of being x is -3 and then the y is 1/8, now I'm going backwards. The x is the 1/8 and the y is the -3. Same thing with the 1 and the 0. Instead of it being x to the 0 is 1, we have the log base 2 of 0 equals 1. And for the most part, you're looking at everything written in an inverse backwards way. Take a look at the graph. It is the same image. It's just been transformed. It's been transformed by a rotation, or you could say it's been and a reflection, or you could say it's been, there's a couple different ways you could say it's been transformed, but basically it's the same graph. There is an asymptote like there was before. This time, because of the nature of the graph, the asymptote is the y-axis. There is a central point as there was before. This time, since it's the inverse, it's not 0, 1, it's 1, 0. And you'll see it goes through at the place 1, 0. It's a very funny looking graph, the logarithmic graph. It kind of finds itself almost like leveling out as you carry on when the x values 8, 9, 10, 20, 30, 50, 100, a million. It kind of looks like a straight line as you carry on towards infinity. And also, as you get closer and closer to the x value of 0, you get closer and closer to negative infinity. It goes down harder, all the way down that way. So this is what we mean by a logarithmic function. And I want to talk to you a little bit about the way you're supposed to say out loud logarithms, because some students make mistakes with that, and it slows them down a little bit with their grasp of how logarithms work. I want you to focus with me first right here at this notation. We'll talk about what that means. You should say that out loud as the log-based A of x. That's what we're going to call that, the log-based A of x. So it's a logarithm, and that means it is an exponent. I'm asking you a very weird question. A to the what power will give you x? That's what that quantity is. It's the answer to that question. So A to the what will give you x? Whatever that value is, that's what the log-based A of x is. And I'll show you some examples of it to make it clear for you. It's easy to understand logarithms if we give you very simple examples up front to start with. And then, as we carry on, you could look at uglier ones with like negative numbers and fractions and stuff like that. So I'd like to start by kind of doing just a couple of basic ones and just kind of get your feet wet with them because it's kind of crucial that we are comfortable with how logs work in order to be able to proceed here. So. All right, guys, I'm going to try to use a couple of examples here. I'm going to try to make this really clear for us. I'm going to ask you while you're paying attention, on the top right, you'll see it says view. Please make sure you click speaker view so that you have a nice clear image of what I'm writing here. I want it to be very clear for you. This is a little tricky, so let's be really clear and explicit here. I'm going to start by talking about some very easy ideas that we all are very familiar with. For example, I know that 5 to the 1 power is 5. I know that 5 to the 3rd power will be 125. I know, of course, that 5 to the 0 will be 1. These are little ideas that I'm familiar with and that are not hard to grasp. All right. Now, I can change those into logarithmic statements. I would say the log whose base is 5 and whose argument is 5 is 1. Meaning 5 to the what power makes 5? The answer is 1. Look how I wrote this. I'm sorry, guys. That's a 5. You know what I'm talking about, all right? Log based 5 of 125 equals 3. In other words, to find out what the answer is, I ask the question, 5 to the what power will give me that 125? I like to draw an arrow going up this way. It makes me feel like I'm answering that question. 5 to the what is 125? The answer is 3. 5 to the what would give you a 1? The answer is 0. So this is what a logarithm is, guys. It's exactly the same idea as an exponent, just written with the numbers 5, 3, and 125 in different locations around the funny formation of it. And I want you to just kind of look at it like a simple idea. We could go crazy and do mean ones too. Like, for example, I do understand that 3 to the negative 2 is going to be 1/9. So you can change that around and say the log based 3 of 1/9 is what? And you should figure out that's -2, So we could go there with it. And you can also do this with fractions, but we're not going to go that far with fractions today. But I just want to make sure that you can see the connection between exponential statements and logarithmic statements. It's really a very basic connection. Just think of it like moving the numbers to different positions so that you can carry out the statement about a logarithm. That's the idea. That's the idea. All right. So once more, for logarithmic functions, when you graph them, they happen to look like that. Just like we said before, for this case, as a reminder, a is a number. Like for our example, a was 5. A common example is the log base 2 of x. There's all the data associated with that. The y-axis is the asymptote in this case because we have one that's centered right at 1, 0. And in this case, the central point is 1, 0 because this is our basic model. Again, you might find it in a different place based on how it was graphed and stuff. And then inverses are the inverse is the exponent. All right. All right. Perhaps my favorite place of all, Ventnor City Beach. I go here about 3 times a week. I was just there on Friday, and wow, what a beautiful beach day. I hope you guys have the chance to come to the beach. In Atlantic City, there's no beach badge, so come and take a swim. Anyway, let's compare them now. And you're looking at the 2 graphs. I wanted to put it together. Basically, you're just looking at kind of cut and paste screenshots of your textbook here. I organized them in this way to make it very clear for you so that you can compare and contrast them. I want the logarithmic function and the exponential function to be a basic connection for you. It's easy, and as you could see, you just kind of switch the roles of x and y. That is, after all, the definition of an inverse, is that you're switching the x and y's. All right. Other things about these functions we want to remember that are important. The asymptotes are different. For the exponential, the asymptote was the x-axis, and for the logarithmic, the asymptote is the y-axis. For the exponential, the central point is 0, 1. For the logarithmic, the central point is 1, 0. And what else? They're inverses of each other. All right. So this is Lake Lenape. It's a nice place to go for a walk, or if you're interested in boating, if you want to charter a boat or go fishing, this is a good place to go from. Let's do some examples now, okay? In examples 1 and 3, they ask you to graph the exponential function. I'm not going to waste our time on this. You have Desmos. We've studied Desmos. You know how Desmos works. Go into Desmos and graph them and get the answers. If you need to get the actual amounts, for some of them, you should be able to figure it out off the top of your head, like 10 to the negative 3. You could see they don't even want you to find a decimal. Just know that it is 1 over 1,000 and so on, okay? Filling in the chart should not be hard. Use the calculator, use Desmos. Right? This is a beautiful trail in Savannah, Georgia. My niece just graduated this year from Savannah College of Art and Design with a bachelor's degree in sequential art, and I'm so proud of her. We go to Savannah all the time to go and see her, and now we won't be going anymore, I guess. She's graduated, so, but anyway, this is a beautiful trail in Savannah that we went on one day. Let's do an application now of exponents. In this case, we're going to give you a function and we're going to tell you a story about the function and then ask you to find specific values of the function based on the story. This came out of chapter 5.1. This is example 2. Future value of an investment application preview. If 10,000 is invested at 6%, compounded monthly, the future value of the investment S after X years can be found using this function here. Now find the future value of the investment after 5 years and after 30 years. It's a straightforward plug-in. I'm sure you've seen compounded interest before somewhere along the lines to become where you are in quantitative analysis as a business student. Plug the number in and get the answer. All the arithmetic is given right there for you. You'll see that they put the 5 in the X value. Notice that they like to use parentheses. I am also partial to that. I'd like to use parentheses to express multiplication when I'm teaching. They're more clear than a times or than a dot. So use your parentheses, okay, if you can. And just go in and plug in those numbers and get your answer. Make sure that you do what's up in the exponent first. In other words, 12 times 5 is 60. Then make sure you figure out 1.005 to the power 60 first. In other words, don't make the mistake of 10,000 times 1.005. You should not do that. You should do 1.005 to the power 60, get that quantity, and then multiply it by the 10,000. And the same thing for 30. So we can say, we can make an extrapolation and say, note that the amount after 30 years is significantly more than the amount after 5 years, a result consistent with exponential growth models. So in other words, if you look at it, obviously, it's a lot bigger when the number is 30 than when it's 5. All right. You're looking at a view from a hotel in Atlantic City. This is probably when we stayed at Showboat or maybe when we stayed at Hard Rock, but this is the Steel Pier. It's a great place for the kids. There's, if you're in Atlantic City, it's about having fun with the adults, but if there are children around, this is a great place to bring them, of course, on the beach during the day, and then at night there's rides. The rides are really a lot of fun, and the Ferris wheel is really beautiful. So I recommend next time you're in Atlantic City, try to check out the Steel Pier. They also have claw machines and hot dogs and a lot of good stuff. So it's a lot of fun. Go there. Example 4, some more applications with exponential functions. Let's look at this. It's about medication dosage and how long it stays in the bloodstream. A little word to the wise here, a little word of caution. Sometimes when you're reading these examples, they're pretty far-fetched and they may not really be something that you're very interested in. For example, I know that the bulk of you are business majors. This is about nursing and biology and anatomy a little bit. It may turn you off a little bit. The point of it anyway is when you see an application, it's a word problem, try to just for a minute, step into the shoes of a nurse or of a doctor and think for a minute, because you only have to demonstrate that you understand how exponential functions work. And it's a matter of finding ways to apply it. So that can be frustrating sometimes when you are not that familiar with the physics or the chemistry or something that is in a word problem. Remember that the title of the chapter is exponential functions, and this is an example of an application with it. So you're probably going to wind up just doing some exponents here. So it's set up to be a little bit direct that way. And the formula that they give you is pretty direct. So let's see if we can make heads or tails of it, shall we? Okay, this is example 4, medications. Each medication has an elimination constant that corresponds to the percent of the medication the body eliminates between doses. Okay, did you get that? In other words, every medication has a certain measurement that has to do with how long it remains in your bloodstream before it's out of your bloodstream. Suppose that for a certain medication taken every 6 hours, the milligrams M present in the bloodstream T hours after a 500 milligram dose is given by this formula. Find the amount of medication in the bloodstream after an hour, half an hour, and after 6 hours. So if you think about it for a while, you'll get it that basically all you have to do is just plug in 1/2 to the value of T, get an answer. Then do it again and plug in 6 in for T and get an answer. And if you look, there's the arithmetic, it's there. This is, again, just screenshots out of your textbook. And the questions in Web Design are going to be almost exactly like this. So just get ready for an interesting story and then basically plug the number in and get some answers. Here's your answers, okay? You can do that with Desmos or with a calculator. Some calculators will do it all in one shot. Again, we talked about how you should use the plus minus key, which is a toggle key. Let's talk a little bit about the enrichment and extrapolation here. It says, note that after 6 hours, the time between doses, about 300 milligrams of medication remains. So about 200 milligrams, which is 40% of the dosage, has been eliminated. This means that the medication's elimination constant is 0.40. I mean, that's really fascinating, but really, do we need to know that and memorize that? No, it's just a matter of seeing how you can use exponents as an application and proving the purpose of it and showing how it does help in very important practical ways, like, for example, medications for people who are sick. Okay, so don't let that drive you crazy when they give you extra stuff there at the end of it. It says the elimination constant is 0.40. Why do they tell you that? Because they're hoping you think it's interesting. You don't need to know that. That's not even part of the story. Also, notice how they told you in the word problem, it says after 500 milligrams dosage. We didn't even need to know that. In fact, they already factored that in. Look at the formula, it has a 500 in it. So it's set up to just be used to put the number in. And usually that is just the case. So look at them that way, my friends. And also try to, learn something about medicine for just a quick minute too. Look at it like that, okay? All right, what you're looking at is El Toro, one of the most awesome roller coasters in the whole wide world. You can find this at Six Flags Great Adventure in Jackson, which is not very far from where you guys are if you're living in a dorm over there in West Long Branch. I recommend you go check it out one day. Make sure you wear sunblock. But it's a great place to go. They have a log flume. They have a Buccaneer ride where it's like a ship that goes back and forth. And it's a really great amusement park. And they have themes, like they have Halloween is really fun there. Anyway, I recommend it. And this is a place called Great Adventure Six Flags. So now we have another case with a special kind of number. That number is E. I'm going to talk to you about E for a minute. E is a number like pi that is irrational. It's 2.72 or so, and it carries on forever like pi. And it was discovered by a German mathematician whose name is Euler. Euler spelled his name E-U-L-E-R. So it looks like Euler, like a ruler, but it's not. It's Euler because of in German, that's how you're supposed to say that name. Anyway, Euler came up with the letter E, or discovered the letter E, and E is used widely through chemistry and physics. It's used most notably as the base for natural logarithms. In other words, the most appropriate base when you're trying to study things with logarithms for many different reasons. But one thing in our class that we need to at least talk about is E is an important number like pi. It's an irrational number. And when you see the letter E, it is not a variable, it's actually a constant, and that constant is 2.72. Now, you don't have to actually write the number 2.72, you can just write E and we know what you mean. And here are some examples now of using E in an exponential function and seeing what kinds of answers and graphs you get. As you can see, it is after all just the same shape. Again, it's a boomerang. It has a central point, 0, 1. It has an asymptote. If you wanted to make the exponent negative, as you could see, it will flip the graph around the y-axis, see the image on the right. And likewise, when you use your calculator, there is an E to the X button or an E to the blank box button that you can use to get different powers of E. when you use Desmos, you could just type the letter E out of your keyboard. It totally knows just what you're talking about. So you don't even have to think about it. You put it in like it's a variable. And of course, Desmos recognizes E and uses the value 2.72 to however many decimal points. So here we have some great examples of exponential functions involving E. You could see where we have on the left there, we're using x values -2, -1, 0, 1, and 2 to get values. If you needed to do that specifically in Desmos, I want to take a minute and show you how to do that now. And we can also talk a little bit about what it would be like to graph the other one too. So let's focus together on Desmos for a minute. Let me go and get my Desmos out. All right, friends, we're looking at Desmos. And I'm going to just coldly type in y equals e to the x. And there's your picture. Okay, let's zoom out a little bit so you can see it. And as you know, it does go on forever to the left. Look how it looks like it is the x-axis. It's not, like we discussed, it's an asymptote, the x-axis. It never touches it. But we're trying to show with drawing that it does get closer and closer to it. It kind of winds up looking like it becomes it, but it's not. All right. Now, if I wanted to get a table of values here, just as a reminder, how would I do that? I would click right here where I have the gear. And then I would say, please give me a table by clicking this table icon right here. And if I wanted to get, well, actually, there's all the values that are in the PowerPoint, -2 through 2. But if you wanted more of them, you could just put in as many as you need. If you want, we could look at the other one, which is y equals e to the -2x. And I'm going to turn off the other one. There you go. Now I'm looking at the purple one, and if I want to get a purple table, a table of the purple graph, I click that and get this. And there's your numbers right there. I could carry on if I want to and get as many as I need. And then you can see, you can point to them, it'll tell you what they are. See? All right. Okay. So I hope we're all okay with E. E is not a big deal. It's just 2.72, and you can type E in just the way you see it, and the calculators and the Desmos will figure it out for you. Now you're looking at a beautiful scene from Florida. We went to Florida, and I think maybe 6 or 7 times we've been to Florida. And I just love going there because I love the weather. I love the scenery. And this is at Ponce Lighthouse. As you can see, I was afraid to go to the top of that, but I would never go up that high into a lighthouse. I'm a little bit nervous. Anyway, so this is Ponce Lighthouse. We went there one day, and I thought this was a beautiful place too, so I included it in today's PowerPoint. And now I'd like to talk to you about regression lines. Okay, remember that we talked about regression. We talked about lines of best fit, and we did lines of best fit for cubic and quadratic and linear models. Now we're going to do them for exponential models. Okay, by the way, you're looking at Asbury Park. This is the Asbury Park Boardwalk. This is a place called the Casino. There's no gambling in there. In fact, there's nothing in there. As of now, there might be something in there. I don't even know. I haven't been there in so long, but it used to be a really, really awesome amusement park in there, and it's at the mainly at the end of the boardwalk there. So I recommend take a walk on the boardwalk in Asbury Park sometime. You'll see that. All right, let's talk about regression with an exponential function. I'm going to read the paragraph, and I ask you to try to follow along with me, and then we'll go through how to get the answers. All right. Historically, prices for goods and services rise, resulting in the erosion of the purchasing power of $1. The table given gives the purchasing power of a $2012 for selected years from 2012 and projected to 2050. With the $2012 as a reference, the 2016 purchasing power of 0.921 can be interpreted as meaning that in 2016, a dollar purchased 92% of the goods it would have purchased for $1 in 2012. So this is the idea of inflation and erosion and all those ideas. And if you're a quantitative analysis business student, you should have been exposed somewhere along the line to this concept. It's a little bit hard to grasp, but it does follow exponential patterns. And you can see here, we have selected years. Notice they said selected years. The reason why they said selected years, guys, and this is crucial, is because don't assume that all the years are in a nice perfect line. For example, look at how it's 2012, 2014, 16, 18, 20, and then 25. 25 is a little bit funny, isn't it? Shouldn't it be 2022 next? The point I'm trying to make is watch out for that when you enter your data. Don't just assume based on a pattern that they're all the same. That's what selected means, not every other. It would say every other year or something like that. Anyway, here we have some years and here we have the values. We're trying to find a trend. So what we're going to do is we're going to use Desmos and plot this data. And when we plot the data, it's going to look like a boomerang is what's going to happen. So instead of it looking like a cubic or a quadratic, which was the parabola, or a straight line, you're going to plot the dots and they're going to wind up looking like a boomerang. You're going to say, oh, this should be an exponential model. And then you're going to use an exponential regression syntax and get your answer. Just like before, we're going to align the data because we have very large years here in the 2000s, so we can align the data. And then we'll put our values in and we'll see what we get when we do a linear regression. Okay, so the first thing is asking you to use this data, use X as the number of years after 2010, and find an exponential function that models the decay of the purchasing power of the dollar. So that would mean that you are going to try to make it, since it's years since 2010, that means this is going to be 2, and this is going to be 4, and this is going to be 6. This one will be 8. This one will be 10. And strange enough, this one will be 15. See how I've aligned the data? I changed all the data to be the number of years since 2010. And now I can use those values for the X and the other values for the Y. I'm going to put them into Desmos and perform a regression. Then part B says, what does the model predict as the purchasing power of 2028? Meaning after I see what the regression line looks like, after I do the syntax and perform the regression, go to that line and look at what the Y value is at 18. Because for 2028, that means X equals 18, right? Okay, that's our plan. That's what we're going to do. I'd like to go right into Desmos and do that for you. But before we do that, I want to reveal the answers here, and then we'll go into Desmos and I'll demonstrate how to do it for you, okay? So you take all the numbers there, you change them by aligning the data like I showed you right there. You put the data in, and then you type in this very important syntax. I want you to look closely at the syntax with me. Y1 is similar to AB to the power X1. Remember earlier I explained to you that we're going to have a real number as the base, and we used 2 in our first example. And I also mentioned that there might be a bonus multiplier in front before you see 2 to the X. That's what the A is. And when you write out a formula using these values, and you'll see that the regression came up with these values, the final model is actually going to look just like this. It will be Y is equal to, and the value A, which is 1.0207, times value B, which is 0.983291, and now to the power of X. That's the actual model based on the parameters that came out when you did your regression analysis. We're going to use that model to look at the graph and find out what the value of X would be in the year 2028, which would be X equals 18. We're going to find the value of Y for that using that model. Okay, so that would mean to go out further here into 18 and figure it out. Let's do that now with Desmos, and I'd like to walk you through the actual methodology of how to do that. Let's go back to Desmos. Okay, and we're going to clear out everything that's in Desmos here. And I'm going to go back to the home, and I'm going to type in some important data. This time, since I'm going straight in with data and not an equation or function, I'm going to type hit the plus sign so I can get a table and start putting numbers straight in. All right. The numbers, if you recall, were 2, 4, 6, 8, 10, 12, and then 15, right? Now here are the numbers: 1, 0.962. 0.921877, 0.829822, Oh wait, this is 15. That's my problem. Okay. All right. Now, I got my dots. Take a look at the dots. Not very clear. Not very clear at all. Let me zoom out a little bit. I don't really kind of see them very well. But I do see that, yeah, look at that. I can't really see how they go, but you don't really need to see them. But it does make the shape of a boomerang. It's kind of hard to see. If you play around with the wrench, you'll get a better picture. Maybe you'll be able to see that it looks like a boomerang. Regardless, you understand the point. The point is put the dots in and then do the exponential regression and see what you get. So let's type in the syntax now. Y1 is similar to AB to the power of X1. Now it looks like a straight line, but if you zoom out, check it. It is ultimately a boomerang. But right now, if you look closely, it does look kind of like a straight line. Anyway, here are your values right here, like I mentioned earlier. And you know that you can use those values to make a new model. So let's type that in. Y equals 1.0207 times 0.983291 to the power of x. And if I take this and change it into a table, I can quickly and easily get the answer to what do they want? They wanted for 2028, which means x equals 18. So you put 18 in there. Here's your answer right there. All right, so let's just review what we did. First, we used the plus sign on the left, and we got a table, and we entered the data. Then after we entered the data, we wrote in the syntax for performing an exponential function, which you see there, y1 is similar to. It gave us values for a and b. Then we constructed the model in a new window, and we have it as its own function. And we can now take that function and change that function into a table and find out what is the value for any x on that line. For example, the x value of 18, representing the year 2028. Our solution is 0.753, meaning that in the year 2028, a dollar would buy 75% of what it used to buy in 2000, whatever, what was it, 2012, 2002? Yeah, 2012. All right. And that's another great example of an application of an exponential model. Very good. All right. So just remember, put it together the right way, and then, put it into Desmos, and you get your solutions there like we showed. There's the model we talked about. And there's the dollar amount, the purchasing power of 66 cents. That's there because there was a change in the way I put the data in somewhere along the lines, but it's supposed to be 75%. And if you look at it, it will come out right. It's because this parameter is different. It came out a little bit different this time. Okay, you're looking at Wildwood, New Jersey, another great place to go in the summertime. And while you're in Long Branch, you're not that close to it. You're kind of a little bit of a stretch from Wildwood. Wildwood is all the way down like mile marker 5 on the Parkway, so it's a good 100 miles away from you. But if you want to go to another really fun, notable beach in New Jersey, that's a great place, Wildwood. Okay, so guys, right now it is 9:54. We're gonna take a short break, and when we're done with that break, we'll come back and we'll talk about chapter 5.2 together, and then we'll finish our lesson for the day. Thanks so much for your close attention to the lesson. Let's take a short break now, and when we come back, we'll talk about chapter 5.2. We're going to take our break until 10 a.m. So it's a good time to regroup, go get a cup of coffee, or go stretch, or if you haven't had breakfast, go get a banana or something, and then we'll be right back shortly in 15 minutes, and we'll go through chapter 5.2.